Okay, this hour we'll talk about how to use Keras to build your own neural network model. So again, the first example is that we like to build a very simple linear model. Okay, y equals a plus x plus b. So the first thing is that you need to create a normalizer. Okay, as we mentioned before, it is somehow necessary for you to add the normalize before you analyze your data. So here's the definition of the normalizer right here. So right here we call it horsepower normalizer, and we simply just use one features in this example. So it has only one feature, which is a horsepower. Okay, so uh, make sure you adapt the normalizer by using the x1 data. Okay, so again, sequential function is how we use Keras to build our network. Okay, so the most important parameter in sequential function is layers. Layers is it is a list of layer. Okay, so basically you can see that is a list, right? So we have two different element. For each element is a layer we want to create. So basically the first layer, it means that we have an input which is x, and we add an additional normalizer on it. So after that, it produce x1 prime, which is the normal scaled x1. And the second layer, which is a dense layer, as we mentioned before, it is dense layer. Okay, the unit 1, that means okay, it has only one following neuron in this dense layer. Okay, so and we know it is y. So basically you simply just connect it. Okay, so in the meantime there should be a weight, the corresponding weight on it. Okay, and also you can name this layer. Okay, this layer, you can name this layer. Okay, the name I write here is linear right here. Okay, and as I mentioned before, if you use dense layer, there's always additional intercept right here. So there is an additional intercept neuron right here, and its corresponding weight should be W0. Okay, although we did not mention it, we did not mention it in here, but default by default, okay, there is an interception right here. Okay, so that is the structure of your network. Okay, and two additional important parameters in your dense layer. One is kernel initiator, and the other is bias initiator. So the kernel right here means weight. Because when we perform when we try to find the smallest value of MSE, right? So basically we have A and B. So A is the weight, right? And B is the intercept, okay? Or we say it is the bias. And the first step is to randomly select one A0 and B0, right, as the starting point. So these two specific parameters, they indicate that how did you select the very first A0 and B0. So the kernel initiator will try to random select, or say, or random generate those weights, and the bias initiator will create the initial bias value, initial B. Okay, So here is again another function provided by Keras, which is the initiator is a random normal standard deviation equals 1. That means you use a normal distribution. Okay, its mean value is 0 and its standard deviation is 1, and it depends on how many different features you have. Okay, and in this example we have only one feature, which is x1, so it will randomly sample one value from this normal distribution as the initial a0. And again, for b, okay, this is another example which is called initializer zeros. That means we simply just use 0 as the initial value of b0. Okay, so if you have, for example, if you have 9 different features, and this function will randomly sample 9 different weights as the initial weight of w1 to w9, and b, okay, is 0. So that's how you construct your neural network. So that is the first step. Okay, so after that, when you write your homework or assignment, okay, you simply just use this value, okay, this function summary, to print all the values, all the structure information of your design. Okay, so it says it has 2 different layers. Okay, the first layer is normalization. Okay, so the output shape right here means, okay, we can move it to this one to here. Okay, so the output value non-1, the 1 means x1 prime, because it only output one feature, right? The none right here means a number of inputs. Okay, because when you design your neural network at the design stage, okay, phase, at the design phase, we don't know how many different data point in your data set, right? Although that is n. So when you print the summary, okay, it will use a non-value to represent n value, okay? Because at the design phase, we don't know that value, okay? And the output will be 1. That is the x1, okay? So at the second layer, okay? So again, right here, that is n, right? And the 1 means y, because the output will be y, right? So think about one thing, is that to output this y, okay, we have 2 different parameters. One is for x1, the other is for the interception, is w0. So we have 2 parameters right here. But take a look at this one. For the normalization layer, we have 3 different parameters. But take a look at this one. Okay, we don't have 3 different weights. But think about one thing. When we try to apply normalization on all x value, you need to know how many different samples you have, and you need to calculate the mean value, right? And you need to calculate the standard deviation of x1, right? So basically you have 3 different values need to be stored in this network. Those networks should, these 3 values should be preserved in your network. So we have 3 additional parameters right here. But those values are calculated by adapt. Okay? They are not weight. They are not W1 and W2. So right here we can see that total parameters right here is 5, but only 2 of them are W1 and W0 right here. They are trainable. Okay, because we need to train this value to find the optimized W0 star and the W1 star to get the minimize the smallest value of MSE. But these 3 value, n, n value, mean value, and standard deviation of x1. They are non-trainable parameters. Okay, that is how you read this summary. Okay, so that is okay. So next thing is, after we have the structures, okay, this cell means we simply just select 10 dataset and feed those 10 dataset into our model. So we put these values. So we simply put these values into our model to perform prediction. And you can see that the prediction is the value, which is the y. But make sure you understand that it is an untrained model, because at this moment, we simply just use A0 and B0 to calculate the y value, because it is not trained. Okay, so you can use the get layer, and you give the name of the layer you want to output. For example, right, this name is linear, right? So the linear is right here. So for the dense layer, okay, for this dense layer, it has two different weight, which is W1 and W0. So we can simply just print. So that is A, that is B. Or we say that is W1 and that is W0. Right? Because B0 is 0, right? And A0 is a random value we sample from a normal distribution, right? So that is the untrained model. So step number 2 is that you need to specify two different things. The first thing is the optimizer. When you perform gradient descent, what kind of strategy you would like to use? Okay, we will introduce several different strategies later, but right here we use the strategy is Adam, and the linear learning rate is 0.1. The learning rate will be used right here. Okay, the Adam means adaptive. Adaptive means when you perform gradient descent, the learning rate will be adapted. So we'll dynamically change the learning rate while you perform gradient descent. The learning rate will become larger or smaller. It depends on where the position, where you are in your MSE basin. Okay, we'll dynamically change the learning rate. Okay, we'll talk about Adam later. Okay, so the next thing you need to specify is what is the loss function you would like to use. You can simply just use MAE or MSE, or if for the classification model, you can use cross entropy. We will talk about several different loss function later, but for regression problem, we simply just use MAE or MSE. For classification problem, we simply just use cross entropy. Okay, we'll talk about it later. Okay, but in this application, we simply just use MAE. Okay, so that is the second part. Okay, the third part is fit. That means we have all the x and y in our training data, and we start performing gradient descent. Okay, but when you perform gradient descent, there are several parameters right here. So the first thing you need to know is that for MSE or MAE, okay, we use all the data point in the training data set to calculate MSE or MAE, right? But here we have an important parameter which is called batch size. 32 means we divide the entire n data point into several different batches. So for example, if the n number, right, for example, okay, just for example, is 1600, so the batch, the number should be 50, right? That means you divide the entire training data set. Okay, make sure that is training data set into several small batches, and each batch has 32 data points, and for example, in this case, you have 50 batches. Okay, so when you calculate MS, when you perform gradient descent, okay, you need a loss function, right? So when you perform gradient descent, you don't simply just put all the entire n data point right here. You simply just use one batch, okay, one batch, 32 data point in your loss function, and perform gradient descent once. And after that, you use the second batch data points in your loss function, and then perform next gradient descent, and so on and so forth, so on and so forth. So for the first run, you have 50 different batches, so you can perform 50 different gradient descent. Okay, so that is how you perform, because gradient descent, because it is much easier to calculate those values. You don't have to use the entire data set to perform one gradient descent. Okay, so we call it one round, right? Because you perform 50 different gradient descent by using different 50 batches. So we call it a run, but usually, okay, the name is called epoch. Okay, so in this setting, we need to run 100 epochs. That means, okay, in total, in this training, you perform 100 different epochs, and for each epoch, you have 50 batches. So in total, that will be 5,000 partial differentiation in your gradient descent process to get the minimum value of MSE or MAE, in this case MAE. So this number of batches, batch size, and the epoch value, and the learning rate, these different numbers, they will they have several different effectiveness to how did you find your smallest value of MSE. Okay, and again, okay, the callback right here, that means after each epoch, what additional process you would like to invoke, but right here is none. Okay, we will show you how several different callbacks later. Okay, but so far it's none. Okay, and there's some important things right here is the validation split. Okay, so originally, okay, we have 100% of data, right? And for here we have test and trend split, right? Right here, and it is 20%. So that means That means, okay, we have 100% data. But for the train and validation and testing, okay, in the first place, okay, we have 20% of data for testing, and those data will not be used for training, right? So we have 80% of data right here. And in this case, okay, if the validation split 0.2, that means 20% of data will be used as the validation data set, and 64% of data will be used as training data. So 60% of data will be used for gradient descent. Okay, so not the entire N data. So only 64% will be used for the gradient descent. And those data will be divided by the batch size. Okay, so that is. So after each epoch, the remaining 60% of the validation data will be used to test what is the performance of the current theta, current weight, current parameters. Okay, we'll show you later. Okay. The validation data none, that means we simply just use the entire training data and randomly select 20% of the data as the validation data. And of course, you can, if you have enough data at the first place, you can divide the entire data set into 3 different data sets: training, validation, test, and you can simply just use your validation data set right here. Then you don't have to split the original training data into 2 different sets, and one for training, one for validation. Okay, if you have enough data, you can prepare your own validation data set by yourself. Okay, so the shuffle, which is the last parameter, that means since we have 100 different epochs, so for the first run, for the first epoch, okay, before you divide, okay, your data into 50 different batches, okay, you have to perform shuffle before split the data into 50 batches. So every time, for every before every epoch, okay, you shuffle the data. Okay, so that is the setting of how you train your model. Okay, so after step number 3, then you have to wait for a certain period of time. Okay, so I add an additional Python magic command right here, which is time. Okay, 2%. Okay, you need this special magic command. Okay, and it will output that some information. For example, when I perform gradient descent, okay, it needs 7 seconds to perform gradient descent. Okay, so we have 100 epochs, and it takes some time. Okay, and after that, okay, and we can see that we can output the information of each epoch. Okay, and we can see that since the loss right here, okay, that is MAE, right? So that means MAE. And that VAL stands for validation. So that is the 60% of data. That's 64% of data. So when we train the 64% of data, and its corresponding MAE value of different epoch is right here. Okay, so we can draw the figure. Okay, so at the first place, because the weight is initialized by some random number, right? So the MAE value, those value will be quite high. But after that, when we gradually move our A0, B0 to some A star, B star, okay? So it takes times, okay? And you can see that the MA value decrease, okay, after we perform certain gradient descent, okay. And as you can see that maybe around 30, okay, and it seems like it is somewhere around the bottom of the MAE, right? Because even if we have more gradient descent, okay, it seems like the arrow becomes stable, right? So maybe it indicates that it can stop the trending maybe at the 40 epoch or 30, okay, because the loss, the MAE value will not decrease, okay, even if you perform more gradient descent, okay. So here, that is the result, okay. We have x1, we have y, and that is the black line is the regression line, okay, found by your neural network model. And here we have the second model, okay. We notice that that is the normalizer, okay. Normalizer has 9 different features. And again, we have a dense layer. So I can draw a figure for you. For example, we have 9 different input value, right? We have a normalizer, so we have a normalizer for each, and it will output the scaled features. And we have the dense, right? The unit is 1, so we have 1y right here. And since it is a dense, so we have w1, w2 to w9. And of course, there is always a intercept, right? So we can draw an intercept right here. That's the w0. Okay, and that is the model of this specific. That's the graph of this specific model. And as you can see that we have 10 different parameters which is trainable, and that is w0 and w1 to w9. Okay, so again, we use MAE as the loss function. We use the Adam, okay, learning rate 0.1 as the optimizer. So we use x and y to perform gradient descent, and here's the result for the validation dataset and the learning dataset. And again, it is a more complex model. It has 9 different features, but still, we after epoch 30 or 40, it becomes stable. So that means we can stop right here. And again, the average arrow MSE, okay, the average MAE is a little bit smaller than the model of if you have only one feature. Okay, the model 1 has only one feature, but this model 2 has 9 features. So we have a better model to predict the MPG, right? So the next model is even more complex. So that is a single input multi-layer and activation. As we mentioned before, sometimes the world is not that linear, so we can use some nonlinear function to model the relationship between your feature and your target. So here we have several different activation functions, which is nonlinear. So here we have 3 different candidate right here. The blue one is sigmoid function. Okay, the sigmoid function is the blue one. Okay, it's very simple. The sigmoid function is something like that. It is an nonlinear function. But as you can see that the range of the sigmoid function is between 0.0 to 1.0 because in logistic regression that simulates the probability, right? So it's between 0 and 1. And as you can see that the slope of this function, it is quite small, right? And here is quite small. Only this part, the slope is a little bit larger. Okay, and as you can see that since if okay, we change it to, and again, that is the definition of gradient descent, right? So if the loss function you choose, okay, is something like you have an activation function and you use something like this one, okay, and a function is your activation function. It is a nonlinear function, okay. If you choose this a function as the sigmoid function, and as you can see that the slope is quite small, so when you do partial differentiation, okay, this part will be quite small because of you choose activation function which at some ranges, okay, the slope is quite small, so the value right here will be small. So that indicates that when you perform gradient descent, okay, when you update your theta, the effectiveness will be not that good if your input value is quite large or quite small. So that is exactly the reason why we adapt normalization before we input our we adapt normalization on our input value, our features. If you use scaled features and your input value will be somewhere around here, and when you use this value to perform gradient descent, and the gradient descent would not that small because it has a slope right here, right? The blue one has a slope right here, has a larger slope right here. So your gradient descent would looks much better. Okay, if you input a very, very large number right here, your slope will become 0, and your gradient descent, this will become very small, right? So your gradient descent will not perform quite well. Okay, so even if the sigmoid function looks so flat, but if you perform normalization first and you still have some slope right here, so when you perform gradient descent on to get a new parameter, a new weight, it still works. Okay, but after that some mathematicians tell us that if you want to perform gradient descent better, you may choose the orange one, hyperbolic tangent. Okay, usually we write it tangent h. Okay, that this function. This function has a larger slope, right? So again, when we do normalization, your input value will be something right here, and the slope is larger. So your gradient descent will perform better. That is a general concept, okay? So that is. So sometimes we will use hyperbolic tangent as our activation function to simulate the relationship, the nonlinear relationship between x and y, okay? So the next one is the green one, which is called ReLU, okay? ReLU is that if the input value is larger than 0, it will simply just output the same value as, okay, the same output value. If your input value is less than 0, you simply just output 0. This, although it looks like linear, but you know it has a technically it is not it is a non-linear. Although it is linear when the input value is larger than 0, but actually it is a non-linear function. Okay, we use it quite often because it keeps the value. Okay, we will show you how it works later. Okay, so here's an example right here. Is that we have a new model. Okay, we have 3 different layers. The first one is the normalization, as I mentioned before. Okay, we have only one x. Okay, the second thing is that we have x1, right, and we have a normalizer right here, so we can output the scaled x1. And here we have 2 additional layers. The first one is we have 12 different neurons, okay, right here. And the layer right here is dense, right? So that is, we have a W1 here, W2 here, and so on and so forth, and W12 right here. And again, since it is a dense layer, so we have an additional 1 right here. Okay, so again, that's B1, okay, B2, B12. Okay, so that is the hidden layer. And again, here we have an activation function right here on this dense layer. That means every time after H1, okay, we have a redo function right here. And at last, okay, we have another dense layer. Okay, and that would be W 1y, W2y to W12y. So that you can see that the H1 equals n redo function and W1 x1 plus B1 and so on and so forth, right? And y equals W1y times H1 plus blah 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 W12y H12. And of course, again, there should be one additional bias right here, so we can write it in this way. By, so there's a by. So that is, you can draw a figure, draw a neural network, and it is corresponding. That is a redo. The corresponding sorry, because we don't have a activation function at the last dense layer, so we don't have activation function right here. So by draw a figure, you can simply just model the relationship between x and y. Okay, so again, we use MAE. We have a add-in optimizer, and here's the summary, right? The 3 indicates the n value, the standard deviation, and the mean value of x1, and we have 24. It's including B1 to B12 and W1 to W12. So we have 24 parameters right here. And at last we have BY and W1Y to W12Y. So 13. So again, it's quite obvious to know what is the number of these parameters in each layer. So in total, we have 37 parameters can be trained, and then we train the result, and here is the training. Okay, and we can see that the result will be like this. Okay, since there are some activation function right here, so the relationship between x1 and y are not pure linear. Okay, so we can see that we have a line right here. Okay, so that's because the redo activation function, okay, sometimes it output value, but sometimes it outputs zeros. So here you can see that it seems like we have two different lines, right? Right, different lines, right? But at this point, okay, at the right hand side, okay, for x1, which is for example larger than 150, okay, part of the neuron output value, you know that is y, right? And you can see that y combine 13 different values from the previous neuron, right? So after 150, okay, the y will be the sum of some neurons at the previous value. But you know some neurons output 0 and some neurons output some positive value. So after 150, only part of the neurons output positive value. And for x lower than 150, some other set of the neurons output positive value and some output zeros. So it looks like this. So that is the nonlinear relationship found by the neural network. Okay, and you can see that at the average MSE is 5, around 5. Okay, so that is one of the configuration of a neural network. Okay, and after that we can perform multiple hidden layer. So you can see that again we have 4 different layers. The first one is in the normalization, and the second one we have 2 different hidden layers, and each one has 64 neurons. So here we have 64 neurons, and here we have another 64 neurons, and all of them perform ReLU activation, and at that we have y. So it is a more complex neural network. So and again we have a loss function, we have optimization function, and you can see that the total number of parameters right here is quite large because we have 64 neurons right here. So total we have 64. There's always an additional B right here. Okay. So right here in this layer we have 4,160 links in this between these 2 layers. So we have a lot of different parameters, and those parameters help us to describe a better relationship between x and y, and so on and so forth. And then we can see that we use here we have right. We have 16% of the data can be our validation, and we have 64 data points as the training data set. And we can see that the lows would be even smaller. Okay, and we have many different activation function to describe the nonlinear relationship. So you can draw it on your on this to describe the relationship between x1 and y. Although we have and you can see that the shape is much more smooth because we have many different neurons. I can guess that we have several different lines right here and several different turning points maybe right here. So that means we have different neurons are activate. Activate means it outputs a value larger than 0. Okay, we have several neurons are activate after ReLU function, and those value will be added to y. Right, so we have 3 different turning point right here. So for the x1 larger than 200, that means we have some set of the hidden neurons are activate, and for some neurons for x between 120 to 200, some other set of neurons are activate, so they contribute to y. And for some for x1 less than 120, some other neurons are activate. Okay, so it depends on how many different sets of neurons are activate to contribute to y. Okay, so again, the last model will be the most complex one because we have 9 different input values, and that we have 2 different layers right here, and they are all dense layers. Right, so I supposedly you know how to read this right now, right? So again, we learn, and we have the corresponding loss value and validation value. Okay, so for those models, okay, we list the average MAE value of different models, and we can see that because of the last model, it uses 9 different features, and it has 2 hidden layers, right? And it has a lot of different neurons, right? So ideally, it should has the best performers. Okay, so take a look at this one. Okay, so you use the best model to perform prediction on test dataset right here. Okay, you use the test dataset to perform, and you can see that the arrow will be smaller compared with some other models. Okay, you can calculate by yourself. Okay, and the last one is that you can save the model because of the weight you trained. You can save those models into a file, and later you can load those weight into the memory and you to perform prediction again. Okay, so I think that is the I provide several different models. Okay, so make sure you understand the how to construct a model, how to use those parameters, okay, and to perform prediction.